So, I'm Dr. Prabir Panja. Today I will discuss about the inner product space with some examples. Actually, in vector space, we have studied several properties of the vectors, basis, dimensions, but there exists no rule to find out the length of the vectors and angle between the vectors in vector space concept. So that's why the study of inner product space is very much necessary. Actually, first I will discuss about the inner product space. Inner product space. Let real inner product space. Let P be a vector space. Any vector space. In R, real vector space. Now let alpha beta be two vectors found in the vector space. And if we define a rule, multiplication rule between the two vectors alpha beta, then under this multiplication rule, V will be in real inner product space if alpha beta satisfies some conditions. Satisfies some conditions. Condition number one. Condition number one is if the product rule alpha beta is equal to beta alpha. The first condition for inner product space. Uh, for all alpha comma beta belongs to the vector space. The second condition for real inner product space will be C alpha C comma alpha C into alpha dot beta that must be equal to C into alpha beta inner product. And what is C here? C is a scalar belongs to the field set R. Okay. And the third condition for the real inner product space is here alpha comma beta plus gamma. Here we are just considering another new vector gamma. Then if we take the inner product between alpha and beta plus gamma, that must be same as alpha comma beta plus alpha comma for all the vectors alpha beta gamma belongs to the vector space. Okay. Now we have the another condition for real inner product space, that is here alpha comma alpha uh, greater than 0 for all alpha belongs to. Okay. Now if any vector space V under the product rule alpha beta satisfies this four property, then the vector space then the vector space V under alpha beta product rule is called the real inner product space. It's called the real inner product space. Product space. Now we'll check a particular vector space will follow real inner product space or not by taking one example. Let us take one example 21. Let R3 be a vector space, and let alpha equal to x1, x2, comma x3, and beta, another vector beta equal to y1, y2, y3, b2 vectors, b2 vectors from R3. Now, if we define the product rule between alpha and beta this way, alpha beta product in a product is equal to x1 y1 plus x2 y2 plus x3 y3. Then we'll check under this product rule are three forms real inner product space or not. Now, so first we'll check the condition number one, alpha beta. Now the value is already mentioned. This is x1 y1 plus x2 y2 plus x3 y3. Okay. If we write now beta alpha, then according to the product rule, its value will be y1 x1 plus y2 x2 plus y3 x3. Now, if we simplify this expression, I think it will be x1 y1 plus x2 y2 plus x3 y3. Since x1 y1 x1 x2 x3 and y1 y2 y3 all are real number, and these are the product between real numbers, so that are commutative. So this value is equal to the inner product between alpha and beta. So the condition one is easily verified. Condition number two. Now, if we take a scalar c, and if we multiply with vector alpha, and if we take c alpha with p inner product, then its uh, value will be equal to cx1 into y1 plus cx2 into y2 plus c cx3 into y3. Okay, this cx1 and cx2 cx3, this is coming from the vector c into alpha, because alpha is x1 x2 x3. So whenever we multiply this alpha by c, C alpha will become uh, C into x1, C into x2, C into x3. Now, this is the value of C alpha comma beta. Now, if we simplify this relation, it will take this form. If we take common C from here, it will be x1 y1, x2 y2 plus x3 y3. So we can easily write this expression as C into alpha beta. So condition 2 is also satisfied. Now we'll check the third one. Let for the third condition, we are taking a new vector gamma as z1, z2, z3. Another new vector. So whenever we do beta plus gamma, it will become y1 plus z1. This will be y2 plus z2, then y3 plus z3. Y3 plus z3. Now, whenever we take the inner product between alpha and beta plus gamma, as per the inner product rule, it will become x1 into y1 plus z1 plus x2 into y2 plus z2 plus x3 into y3 plus z3. Okay. Now, if we simplify this expression, uh, it will take this form: x1 into y1 plus x2 into y2 plus x3 into y3, and plus we can write x1 z1 plus x2 z2 plus x3 x3 z3. Now, if we see this expression, uh, this is nothing but the inner product between alpha and beta. Plus, now if we see the second expression, and this is the inner product rule between alpha and gamma. So we can see that the inner product between alpha comma beta plus gamma becoming alpha beta inner product plus alpha gamma inner product. So we can say the condition number 3 is also satisfied. Now we'll go for condition number 4. For condition number 4, we will take the inner product between uh, two same vectors. Now it will be x1 into x1 plus x2 into x2 plus x3 into x3. So it will be in square form: x1 square plus x2 square plus x3 square. And this value will be always greater than 0 whenever alpha is non-null vector. This will be always greater than 0 if alpha is not equal to a null vector theta. So from this result, we can see the product rule alpha beta satisfies the four conditions for real inner product space. So ultimately, we can say that the product rule alpha beta in the vector space R3, vector space R3 forms a real inner product space. Inner product space. Okay, so this way we can define real inner product space, and this is one of the example that follow real inner product space. Now, standard standard inner product. Standard inner product. See, suppose we have two vectors, right? Alpha, beta be two vector from n dimensional space R to the power n, and alpha is equal to x1, x2 dot xn, and beta is another vector, that is y1, y2 dot yn. These two are from n dimensional space. Now, the inner product rule, if we define this way: alpha beta equal to x1 into y1 plus x2 into y2 plus dot dot in this way xn into yn. So that inner product will be called, that inner product alpha beta is called standard inner product. Standard inner product. So whenever no product rule will be defined in the question, we always consider this standard inner product to solve the problem. Next, we have complex inner product space. Inner product space. Complex inner product space. Suppose let V be a vector space. Vector space in C. That means here the field is complex number. So if we are defining a vector space V over a complex field C, and let alpha beta be two vectors from D set. Then if we define a product rule alpha beta, that is the inner product between two complex vectors alpha beta, then if this alpha beta satisfies some condition, then the vector space V under this product rule alpha beta will be called complex inner product space. Then the alpha beta in the vector space V, if the vector space V follow some properties or conditions, you can say properties, uh, then V is called the complex inner product space. Inner product space. Complex inner product space. Now the condition is first condition is the inner product between alpha comma beta, that must be equal to the inner product of beta alpha conjugate. That indicates the complex conjugate of beta. So here alpha beta are from vector space V, and beta alpha bar beta alpha bar indicates uh, the complex conjugate of beta alpha. The complex conjugate of beta. So this is the first condition for complex inner product space. Now the second condition is if we take a constant C and multiply with alpha, then if we take inner product with beta, that value must be same as C into alpha comma beta, where for all alpha beta belongs to the vector space V and C is a complex constant. Complex constant. Okay, so this will be the condition number 2 for complex inner product space. Now, if we take the third condition will be alpha comma beta plus gamma, that will be equal to alpha comma beta plus alpha comma gamma, and here all alpha beta gamma belongs to the vector space V. Now condition number 4 for complex inner product space will be alpha comma alpha greater than 0 if the vector alpha is non-null, and theta is the null vector in V. Okay, so if the vector space V under this product rule alpha satisfies these four conditions, V will be called the complex inner product space. Now, by taking one example, we'll check a particular product rule will be a complex in a product space or not under the complex number set C. So let us take one example. Let C is a set of complex number. Set of complex number. Okay, and we are defining an n-dimensional Cn this way: Z1, Z2, Zn, where each Zi belongs to complex number set. Then let alpha be vector x1, x2, xn, and beta another vector y1, y2, yn from Cn. Let us take these two vectors from Cn, and if we define the product rule and we define the product rule alpha beta this way, alpha beta value will be equal to x1 into y1 bar plus x2 into y2 bar plus the dot xn into yn bar. Yes. Now we'll check that this n-dimensional complex space C to the power n under this product rule will follow complex inner product space or not. So we'll check these four conditions for complex inner product space under this product. The first condition one, alpha beta. The inner product between alpha beta is already defined: x1 into y1 bar, x2 into y2 bar, same way xn into yn bar. Now, if we arrange the terms uh, this way, y1 bar into x1 plus y2 bar into x2 plus dot yn bar into xn. And if we use the general concept of complex conjugate, uh, we can easily find out these things: y1 into x1 bar plus y2 into x2 bar plus dot yn into xn bar, that will be whole bar of this number. Now this is nothing but we can take b alpha whole bar. Okay, so this is the general concept from the complex conjugate, because we know that Z1 plus Z2, Z1 and Z2 are two complex numbers. Z1 plus Z2 bar will be equal to Z1 bar plus Z2 bar. Okay, same way Z1 bar whole bar must be equal to Z1. Same way we can define these things: alpha beta as beta alpha whole bar. So we can say condition one is satisfied. Now we'll go for the condition number two. Condition number two is C alpha comma beta. So This will be uh, if we multiply alpha vector with c, it will be c into x1, then y1 bar plus c into x2 into y2 bar plus dot dot c into xn into yn bar. Now, if we simplify this result, uh, this will be taking common c, x1 into y1 bar plus x2 into y2 bar plus dot dot xn into yn bar. So the expression within the first bracket, this value is nothing but the inner product between alpha comma beta. So we can say that the inner product between C alpha comma beta is becoming C into alpha beta. So condition 2 is also satisfied. Now we'll go for condition number 3. For condition number 3, let us take another new vector here, gamma. Gamma is Z1, Z2, this way up to Zn. We form the n-dimensional complex space Cn. Now, if we take the inner product between alpha comma beta plus gamma, so this value will be equal to x1 into y1 plus z1 bar as per the product rule. Same way, the second term will be x2 into y2 plus z2 bar. And in this way, if we go to the nth term, so it will be xn into yn plus uh, zn bar. Okay. Now, if we simplify this expression by using the simple complex number concept, conjugate of complex number, so this will be x1 into, we can separate it by y1 bar plus z1 bar plus x2 into y2 bar plus z2 bar. Same way, we can write xn into yn bar plus z. Now, if we arrange all the terms, so this will be x1 into y1 bar plus x2 into y2 bar plus dot dot xn into yn plus second term will be x1 into z1 bar plus x2 into z2 bar plus dot dot xn into zn. Now, if we take the first expression, this is nothing but the inner product between alpha and beta, and the second expression is the inner product between alpha and gamma. So our third condition is also satisfied by the inner product rule. Now we'll go for the fourth condition for complex inner product. So alpha value is already defined. Alpha is x1, x2 dot dot xn, a vector from n-dimensional complex space. Now, if we take the inner product between the same vector alpha and alpha, so as per our product rule, this will become x1 into x1 bar plus x2 into x2 bar plus dot dot xn into xn bar. Now, if we use the simple definition of complex number, so we know that z into its conjugate is nothing but mod z square. So using this concept, we can write this will be mod of x1 square plus mod of x2 square plus dot mod of xn square. So we are getting this result from z into z bar equal to mod z square. Just using this, we can get our result. Now this whole expression will be obviously uh, greater than 0 since alpha is non-null. Non-null. Okay, so we can see that the product rule alpha beta satisfies all the four condition of complex in our product space. So ultimately, we can say that the vector space uh, C n-dimensional the complex plane C to the power n the product rule under the product rule alpha comma beta satisfies satisfies the complex inner product space conditions. So we can easily say that the n-dimensional space C to the power n will be a complex inner product space. This is the end of today's lecture.